Okay, so this is our practice exam for exam 2. Remember that this is just a sample of the kinds of questions that I could ask on your exam. You should be doing this exam without your notes and without any internet support or any help in any way to really gauge how well you know the material. Okay, so let's get started. Number one is the definition of a p-value. That's one of the only definitions that I ask you to memorize this semester. So the p-value of a hypothesis test is the probability of seeing a test statistic that extreme or more in the direction of the alternative, given that the null hypothesis is true. So B is the correct answer here. So direction of the alternative, given that the null is true. All right, the interpretation of a hypothesis test is always about the parameter. We use our statistic to gather our evidence to say something about the population, but the interpretation then is about the population, so it's about the parameter. All right, the power of a statistical hypothesis test is the probability of rejecting the null given that the null is false. So power is something that is a good thing. It's something that you want to be high, okay? Now, you also need to know the definition of a type 1 and type 2 error. So let's find those answer choices here. So what's a type 1 error? Well, that is the probability of rejecting the null hypothesis given that the null is true. So that's your alpha level of your test. So that's a type 1. Type 1 error rate is the alpha level of your test. And then remember that power and beta, the type 2 error rate, there's events that lead to those are complements of each other. And so if power is the probability of rejecting the null given that the null is false, beta is the probability of failing to reject the null given that the null hypothesis is false. So this guy right here is a type 2 error. So know those definitions. You'll need to know those for your test. All right, what's the relationship between confidence level and the width of the interval? They go in the same direction. So a 99% interval is going to be wider than a 95% interval. How would a 90% interval compare to a 95% interval? It would be narrower. So higher confidence, wider interval. All right, and then how does sample size affect the width of a confidence interval? Increasing the sample size reduces variability, so it makes your interval narrower. So sample size and the width of the interval go in opposite directions. All right, what's a good strategy to increase power? Get a bigger sample size. Okay, you can monkey around with the type 1 error rate, but that's not what we do in practice. You can choose your type 1 error rate and then play with the sample size to increase your power. And of course, you can't decrease the population variance. That does affect power, but you don't have any control over that. So get a bigger sample size. That's a good way to increase power. Getting a bigger sample size fixes lots of things in statistics, except for bias. All right, suppose you've conducted a statistical hypothesis test and it results in a p-value of 0.1 and your alpha is 0.05. What should you do? Well, the p-value here is 0.1, which is bigger than your alpha level, right? The p is not low, so the null does not go. So we're going to fail to reject the null hypothesis. Do not find for the alternative. Now, if your p was lower than your alpha, then you do this one right here. Reject the null and find for the alternative. Notice that answer choice B is never a correct answer under any circumstances, and neither is answer choice D. You either reject the null and find for the alternative or fail to reject the null. You don't find for the alternative. All right, so if you carry out a hypothesis test and your conclusion is to fail to reject the null, you could have possibly made an error. And that type, if you failed to reject the null, would be a type 2 error. This is never the answer choice. We don't ever know that a type 1 or type 2 error was definitely made or that was definitely not made. So if you reject the null, you might have made a type 1 error. And if you fail to reject the null, you might have made a type 2 error. All right, so your 95% confidence interval for mu1 minus mu2 is 3 to 5. For the test of the null hypothesis that difference is 0 against the alternative of not equal to 0, at an alpha of 0.05, we would think this difference is statistically significantly different from 0 because our confidence interval doesn't include 0 as a possible value. So if your confidence interval doesn't contain your null hypothesized belief of that parameter, then you think it's statistically significantly different from that null hypothesized belief, and you would reject the null hypothesis. If your confidence interval contains 0, then you would fail to reject the null hypothesis. All right, your 95% confidence interval for mu1 minus mu2 is 3 to 5. How do you interpret that? Well, if I subtract mu1 minus mu2 and my possible values for my difference are all positive, that means I think that mu1 is bigger. So we're 95% confident that the mean 1 is bigger by somewhere between 3 and 5. If these were both negative, -5 to -3, then we would think mean 2 is bigger, so B would be the answer. And if one of the endpoints was negative and the other one was positive, then we would start with this answer choice C, something like with 95% confidence, we're unsure that there's a difference. Okay, so identify the hypotheses. If the Darla Moore Career Center wants to study whether mean salary is different for male and female graduates of the business school, what's your correct null and alternative hypothesis? Well, the null hypothesis always gets always gets the equal sign. And your alternative hypothesis is what they're studying. So we're looking here for a difference. And so that's your not equal to alternative hypothesis. All right. So A is the answer there. And then if you want to study whether the percent of students who go on to have successful careers is higher than 75%, then it's a test about the proportion. So you've got P as your parameter. The null hypothesis always gets the equal sign, so that doesn't help us out very much. The alternative hypothesis is what you're looking for evidence for, and we're looking for higher than 0.75, so C is our answer. All right. All right, so you study whether the percent of students who go on to have successful careers is higher than 75%. If the p-value is 0.005, that's a really low p-value, so that gives you evidence to reject the null and go with the alternative. And so there is strong evidence that the percent is higher than 75%. So E is the answer there. All right, and how about if you did that same study, but you got a p-value of 0.15? Then you got a high p-value. So then you're not going to reject. The p is not low, so the null does not go, and you don't find for the alternative. So here, there's little to no evidence that the percent is higher than 75. So again, the only two conclusions you can make in a hypothesis test are finding evidence for the alternative or not finding evidence for the alternative. All right, so if the test statistic for that test is 2.9, which area would you shade to get the p-value of the hypothesis test? Well, remember that you plunk down your test statistic and then you shade in the direction of the alternative. And the alternative is that p is greater than 0.75. And so you're going to shade the area to the right of the test statistic. So B is the answer. All right, in a design of experiments, when you have k factors, each with 2 levels, you have what's called a 2 to the k factorial design. This comes from that other topics set of your lecture notes in ANOVA. So make sure you know those definitions in there. All right, so in regression and ANOVA, you can check which assumptions with a residuals versus predicted plot. You have 4 assumptions, right? The errors are independent, have mean 0, have equal variance, and are normally distributed. So the independence assumption is one that I didn't teach you any plots for because it varies according to what situation you're in. So the 2 assumptions that you can check with the residuals versus predicted plot is errors having mean 0 and having equal variance, so both B and C. And the assumption that you can check with the QQ plot of the residuals is that the errors are normally distributed. Another thing to keep in mind that we taught you is if your errors are from a normal distribution, what should that QQ plot look like? It should be linear. It should be a straight line. So keep that in mind too. All right, the plot at the right shows this extreme point right here. That's California in our gas tax data set from Regression. What would that point be considered? Well, it's not going to have a high residual because the line would pretty much go right through it. And even if we removed it, it wouldn't change the line. So it's not influential. It doesn't have a high residual, but it does have high leverage because it's far away from the other points in the x direction. All right, and then the correlations in these plots are negative 0.71, negative 0.06, positive 0.72, and positive 0.9. And we want you to identify which plot has a correlation of 0.72. So the two positive correlations are plot A and plot D. D is tighter to a linear form, so that's going to be closer to 1. So D has a correlation of 0.9, and A has a correlation of 0.72. Let's do the two negative correlations real quick while we're here. The correlation of negative 0.06 is going to be this plot here that looks like not tight to a linear form at all. That correlation is close to 0. And then negative 0.71 is this plot because it's a negative relationship. If you fit a line to it, it would have a negative slope. It would go downhill. And it's tighter to a linear form. So it's closer to 1. All right. Scroll here. Okay, so now we've got some output. So notice that we've got an ANOVA. I fitted my model and called it fit. I've got the AOV, call for an ANOVA. And then I've got my Y variable, case price, because that's the thing that comes before the tilde. And then I put the tilde, and I've got my X, my predictor. So location is my predictor. And notice that I've got 3 categories of location. I've got 3 regions. All right, so I've got my output, and then I also ran a Tukey's HSD for multiple comparisons. All right, so our question, first one is, which region had the highest average case price? Well, you can tell that from the Tukey's output. Right here, we can see that Keuka minus Cayuga has a positive difference, positive 24. So that means Keuka is bigger. Seneca minus Cayuga is negative, so that means Cayuga is bigger in that comparison. And then Seneca minus Keuka is negative, so again, Keuka is bigger. So Keuka is bigger than Seneca, Keuka is bigger than Cayuga, so Keuka is the highest. All right, what are the degrees of freedom for location? So remember, in our ANOVA table, on the top row is always going to be the between groups numbers, variation, and sum square, mean square, degrees of freedom, all that. And then the residuals row, this bottom row, is your within. Okay? So the degrees of freedom for the factor is your number of factor levels minus 1. And remember we said we had 3 levels because we have 3 regions. So the degrees of freedom for that are going to be 2. All right. Also remember that your mean square is your sum square divided by its degrees of freedom, and that your F value is the ratio of the 2 mean squares, the mean squared between divided by the mean squared within. All right, so the next question that we have is, how is the F statistic calculated? Well, I just talked about that. That's our mean squared for between divided by our mean squared within. All right, so know how those numbers are calculated. All right, what's the null hypothesis for this ANOVA? Well, remember the null hypothesis in ANOVA is that all the means are equal. So A is going to be the answer. And the alternative hypothesis is that at least one is different. So be able to recognize either one of those. Now, for a significant p-value on a one-way ANOVA, what should you do? Well, a significant p-value means that you have evidence for your alternative that at least one of the means is different. So certainly we wouldn't want to scrap the data. We'd only do that if we failed to reject the null hypothesis, if we had a big p-value. It doesn't make sense to remove an interaction because there's only one predictor here in a one-way ANOVA. There's nothing for that predictor to interact with. And then Tukey's is just one method of multiple comparisons that you know, and that's a good thing to do when you have a significant p-value. You want to find where the differences are. All right, so here's our next question. So here we have an error that is done while machining dental drills. And so If you've ever had a root canal, you know how important it is that their little tools are very, very precise, okay? And so this company that manufactured dental drills was experiencing problems with a specific part on the production line, and they suspected a machining problem that resulted in the length of the part varying outside of the target specification. The machine setting had 3 levels, and there were 3 levels of shift that were evaluated as factors. So here we have a two-way ANOVA because we've got two categorical predictors. And then the deviation in specified size was measured in microns. So that's our quantitative response. All right, we're going to use the output above. So how many times was this experiment replicated? Well, we can tell that by looking at the data set. So notice that at setting 1, combined with the morning shift, we have 3 observations. Setting 1 combined with the afternoon shift, 3 observations. Setting 1 for the night shift, 3 observations. Setting 2 for the morning, 3. Setting 2 for the afternoon, 3 observations. As you can see, at every combination of factor levels, we have 3 observations. That means the experiment was replicated 3 times. All right. And then what's the p-value for the machine setting factor? What I'm checking for here is to make sure that you know how to read ANOVA output. This is the row for my setting factor. That's the row for the shift factor. And this is the row for the interaction between setting and shift. So my p-value there is 0.004522. And then using the p-value for the interaction, is it significant? Now, the lines, do cross here in my interaction plot. So you might think there might be a significant interaction, but the p-value tells us otherwise. It's really high, 0.858. And so that's certainly not a significant interaction. And so what I did was I took it out and reran the model without, which we'll look at that in a second. So which machine setting had the smallest errors on average? Well, this time I can just look at my plot. I can see that setting 1 here is the lowest on the y-axis. So setting 1 has the smallest error. Setting 1. All right. So I ran Tukey's after I removed the non-significant interaction, and we've got our differences, all the pairwise differences for the machine setting, 2 versus 1, 3 versus 1, and 3 versus 2, and all of my differences for the shift factor, morning to afternoon, night to afternoon, and night to morning. All right, so based on the Tukey's output above, which 2 machine settings are not significantly different? So my machine setting comparisons are up here in this set. And so which ones are not significantly different? Well, my only high p-value is this one, 0.887. So that's setting 3 versus setting 2. So 3 and 2 are not significantly different. And then based on the output, the Tukey's output, which shift has the highest average error? Well, again, we can just compare. Morning minus afternoon is negative difference, and so that means that afternoon is bigger. Night minus afternoon is positive, so that means night is bigger. And night minus morning is positive, so that means night is bigger. So again, night is bigger than afternoon, night is bigger than morning, night has the biggest average error. All right, based on the output, what's the interpretation of the confidence interval for the night to morning shift comparison? We're 95% confident. Let's see. So night to morning, it goes from 1.15 to 3.54. So we're 95% confident that night shift has a higher error by between 1.15 microns and 3.54. So let's see what answer choice says that. That's right here. We're 95% confident that the mean error is 1.15 to 3.54 microns higher for the night shift. All right. And our regression output. So you're going to have some ANOVA questions on your actual test, and you're also going to have a set of regression questions. So make sure that you know all of these topics and do all your extra practice homework. All right, so let's get to it. Looking at the scatter plot, the correlation coefficient R for these data should be what? It's going to be negative because this is a downhill relationship that's showing in this plot. All right, and then find the prediction of congestion costs per person for a peak freeway speed of 40 miles an hour. So the first thing you should do before you make a prediction is make sure that that value of X is within the range of the X's that you collected. And it is, 40 is, we did have observations around 40. And so we can make a prediction simply by plugging in that value to the regression equation. Now, what is the regression equation? We can get that here from the output. So you get that from your estimates column. So the estimated congestion cost, that's the thing on the y-axis over here, is 125.157 minus 1.98, because we have a negative 1.98 for the speed coefficient, times the speed. And so to get a prediction of the congestion cost at a speed of 40 miles an hour, just plug in 40 where it says speed. So this is the answer, A. And then we are asked to find a prediction of congestion cost per person for a peak freeway speed of 70 miles an hour. All right, so the first thing we have to do is look and make sure that the number we want to predict from is within the range of the x's that we observed, and it's not. 70 is off the chart over here. So that's going to be an extrapolation. So you shouldn't predict based on a speed of 70 because we don't know what the model would look like out there if we were to collect data. That's called extrapolation. All right, identify and interpret the standard error, and then identify and interpret the R squared for the regression. Okay, so what's the standard error of the regression? That is this residual standard error. These standard errors up here are for your coefficients, so you can get your t-test statistic and your p-value to test those. The standard error of the regression is called residual standard error, and it's 7.27. Which R squared are we going to use? The multiple R squared. Remember, we're going to use this adjusted R squared when we get to multiple regression, but not yet, because we're only doing simple linear regression right now. All right, so the residual standard error is 7.27. That's your measure of variability around the regression line in the y direction. So what's on your regression line? Predictions. So one interpretation is that predictions of congestion cost tend to be off by $7.27. All right, so that's the variation around the line. Remember, it's always about the y. And then the R squared is 0.8479. So roughly 85% of the variation in your y in congestion cost is explained using this regression model. All right, remember these are both, it's always about the y. You're predicting the y, you're talking about the variation in the y, it's always about the y. So the standard error of the regression is going to be this one. It's not E because we're not predicting the x, we're predicting the y, congestion cost. And then for the R squared, it's this one, 84.79% of the variation in the y is explained using our regression model. All right. Plugging in 30 to the regression equation does what? Well, it gets you a prediction. We've already played that game, right? But what does that mean? Well, that prediction is the average y at that x. And so you're getting an estimate of the average congestion cost per person. So I just want you to really understand that regression line. All right, interpret the slope of the regression equation. Remember, it was negative 1.98. So that means if we put it over 1 for the x's, the x's are miles per hour and the y's are dollars. So negative $1.98 divided by 1 miles per hour is interpreted as for each additional 1 mile per hour of highway peak whatever speed, the y's go down, they decrease. The congestion cost per person decreases on average by $1.98. So that looks like D is my answer choice. We expect congestion costs per person to decrease by $1.98 for each additional 1 mile per hour in peak freeway speed. All right, and then 40, a 95% confidence interval for the mean response at a freeway speed of 40 miles per hour is $44.20 to $47.72. So which interpretation is for the average y? Well, it's not answer choice number 1, because that looks like I'm interpreting a slope for each additional 1 in the x direction. We would talk about how the y's change. That's not the interpretation for the mean response. So answer choice B says we're 95% confident that for any single randomly selected x, peak period freeway speed of 40 miles per hour, the y, the 1y, will be between $44.20 and $47.72. This one's for a single y. And remember we said A is how it looks when you're interpreting the slope. C is the one that we want. C is our answer. We're 95% confident that for peak period highway speeds of 40 miles per hour, mean congestion cost, mean Y per person will be between $44.20 and $47.72. Now, another thing I want you to be able to recognize when it comes to these intervals for predictions or an interval for the slope is if your predict function, you know the predict function that you practiced in your Connect homework, if it has interval equals prediction, that means it's an interval for a single y. And if it says interval equals confidence, then it's for the average y. Also know that the confidence intervals for the single y are going to be wider than the confidence intervals for the average y. And also the further you get out in the x direction from the mean of the x's, both of the intervals will get wider. Okay, so that's it. Good luck on your test and message me with questions.